In this video, we take a look at matrix multiplication. So here's an example from section 2.1 in our textbook, where they give a context to the idea of matrix multiplication to help us understand this. So our first matrix is showing the three concession areas in a football stadium: the south stand, the north stand, and the west stand. So these are the three rows corresponding with the three different locations in the stadium where they're selling food. And then the columns correspond with the top selling items: the peanuts, the hot dogs, and the sodas. So because we're trying to arrange two different variables, that's why we have a two-dimensional representation here with the matrix. So we can see the most peanuts were sold at the north stand, the most hot dogs are sold at the south stand, just by looking at the different columns. All right, the column vector to the side is the selling price for each of the peanuts, hot dogs, and sodas. So we are going to use these matrices to find the total sales of these top three selling items at each of the stands. So we're going to go through some multiplication here. So to figure out how much the south stand is selling worth of peanuts, we take the 120 and we multiply it by the $2 because peanuts sell for $2. And then to figure out, well, how much is the south stand selling for hot dogs, we take the 250 hot dogs times $3 per hot dog. And for the sodas, we take 305 sodas multiplied by 275 per soda. So that's these calculations right here. So we're taking the quantity from the matrix and multiplying it by the selling price in the column vector to get the total of the south stand sales. So if you visually look at this, we took the entries in the first row and multiplied each of them by the column. Now let's move on to the second row. So we take each of these north stand values and we're going to multiply those by the column. So you can see down here, we have the quantity of peanuts, hot dogs, and sodas, each multiplied by their corresponding selling price. So it's kind of like we took the north stand row from the first matrix and kind of picked it up and tilted it and multiplied it by each value in the column vector for selling price. So this is the essence of matrix multiplication. And you can see that same principle at work here with the west stand counts multiplied by the column vector again. So each row separately gets multiplied by the column vector here, and that's our last result here. So what did they have to have in common for this to work? Well, the number of columns in our first matrix had to equal the number of rows in the second matrix. So our first matrix here was a 3x3 matrix, and we were able to multiply that by a 3x1 matrix. And the magic that makes that work is that the number of columns in the first matrix is equal to the number of rows of the second matrix, because of the way the multiplication works here. All right, you could write it out more simply in this form down here. And then you see here's our resulting values. So the resulting values is a 3x1 matrix here, because we took each of the three rows and multiplied it by the one, well, we took a 3x3 matrix and multiplied it by a 3x1 matrix. So you can think about the fact that there's three rows here and one column over here. So we get this resulting 3x1 matrix. So let's take a look at another example. Here's a formal definition for matrix multiplication. So if matrix A, and you can write it as capital A or in the bracket form, A with subscripts ij, where I and j circulate through all the indices. So for example, back here, entry A11 would be here, entry A12 would be here, etc. So that's what each entry is represented by the Aij subscript, where the i's go through all the rows and the j's go through all the end columns. And then matrix B is going to be an n by p matrix. So notice, for multiplication to work, we got to have the same number of columns in the first matrix as we have rows in the second matrix. Then our product is going to be an m by p matrix. So the number of rows from the first matrix and the number of columns from the second matrix. And then we've got in summation notation here written how we multiply each entry. The important thing to notice here is that in this first entry, we've got the first column from matrix A and first row from matrix B. And then here, second column from matrix A and second row from matrix B, and so on through all the indices. So in our example, we've got a 4 by 2 matrix for what I'll call matrix A. And matrix B is a 2 by 3 matrix. So we are in business because we have the same number of columns in matrix A as we do rows in matrix B. And we know our resulting matrix is going to be a 4 by 3 matrix. Based on these dimensions right here. 4 rows in column A and 3 columns in 4 rows in matrix A and 3 columns in matrix B. All right, so I put some more space here so I can work out our example by hand. And then we'll go see how to do this calculation in Simpy. Okay, so for my first calculation here, and I'm going to go slow because I'm likely to make arithmetic mistake in here somewhere. We are going to take 2 times 4. And then we are going to add to that 3 times -2. That very first entry, I'll keep a running entry down here, is going to be 8 minus 6. So that's going to work out to be 2. All right, and then our next entry is going to be 2 times 1 plus 3 times 1. So that is going to be 2 plus 3, or 5. And then our last entry in the first row is going to be 2 times 0 plus 3 times -5. So 5 there. All right, so that's going to be 0 minus 15. And so we get a -15 here. When you are working matrices by hand, it's not necessary to write all these intermediate steps like I am. I am doing this just to help illustrate how you do this by hand. I'll try to clean up. I tried to use a docker for multiplication, but I think a parentheses is a little more clear. All right, let's switch to the next row. I'll switch colors over to, let's see, black should show up okay. So our next row is -3, 2 in the first matrix. And our column corresponding with that is 4, -2. So we're going to have -3 times 4 plus 2 times -2. And then that's going to be -12 minus 4, which works out to be -16. All right, our next calculation is going to be -3 times -3 and 2 multiplied by the column 1, 1. So we'll have -3 times 1 plus 2 times 1. So that's going to be -3 plus 2. for negative 1 is my calculation here. Then our next calculation is negative 3 times 0 plus 2 times negative 5. And so that works out to be negative 0 minus 10 here. So we get a negative 10 over here. All right, halfway done. So let's switch colors. I'll do red now. And so now we're going to work with the negative 3 row. We're going to have negative 3 times 4 plus negative 3 times negative 2. So notice as I'm doing these calculations here, all of the values in this resulting column, the 4 and the 2, or the 4 and the negative 2, come from the first column of our second matrix, and then the 1, 1 from the second matrix you see over here in the calculations, just so you kind of visually see what's going on there. And then the 0, negative 5 from that third column in the second matrix is showing up in this third column calculations of our resulting matrix. And then similarly, you see the 2, 3 carried across the rows, the negative 3, 2 carried across the rows here. And to make life a little easier, I'm going to switch this out instead of saying plus negative 3 to just say minus 3 times negative 2. All right, so that's going to give me a negative 12 plus 12. So I think I'm going to get a, instead of 12, a negative 12 plus 6. So I think I'm going to get a negative 6 here. And then our next entry is negative 3 times 1 minus 3 times 1. So that's going to be negative 3 minus 3. So that is another negative 6 in the resulting matrix. And then we're going to do negative 3 times 0 minus 3 times negative 5. That gives us a 0. Okay, and our last calculation for row 3 of our resulting matrix is going to be the 0 plus 15, it looks like, which works out to be 15 here. All right, one more row of calculations to go. I'll use this color blue since I haven't used it yet. And so we are multiplying 2 times 4. And then we're going to subtract 5 times negative 2. So that's going to be 8 plus 10. With the resulting calculation here for 18. All right, and then our next calculation is going to be 2 times 1 minus 5 times 1. So that's a 2 minus 5, or a negative 3. And then our next calculation is 2 times 0 minus 5 times negative 5. And so that's 0 plus 25, which works out to be 25 in our resulting matrix on here. So our resulting matrix here is a 4 by 3 matrix, just as we predicted here in our earlier screen. So you can make a note, 4 by 3 down here if you want to include the matrix dimensions. So that took me a while. So we are going to definitely save time with matrix multiplication by multiplying in SIMPy here. So let's head over there, and we're going to enter matrices A and B, as I call them. I'm going to say A equals matrix, and then the first row is 2, 3, and the second row is negative 3, 2. The next row is negative 3, negative 3, and the last row, matrix A, is 2 and negative 5, and then close it off with my parentheses. And then I can type A here to check my resulting calculation. And it's a match for what I was working on by hand. And then I'm going to enter matrix B. start with the parentheses. Anytime you do a function in Python, you have to have parentheses. That's common in most programming languages. And then in the brackets, we enter the values for the rows. All right, and then we go ahead and hit enter here. So if I want to multiply here, I am going to multiply A times B. So I'll do A star B, and I should get a resulting matrix that matches by hand. Let's look what happens if I try to do matrix B times matrix A. I get a dimension error mismatch. You can see here the last line tells me I've got a shape error, matrix size mismatch, and you can't multiply a 2x3 matrix by a 4x2 matrix. But as we saw, you can multiply a 4x2 matrix by a 2x3 matrix. So you can do some matrix multiplication practice by hand and then check your calculations using SIMPy.